So to calculate MAPE, we're going to take our deviation, divided it by our actual, which will give us our percentage. So let's go ahead and do that. So let's take our error here. We're going to divide that by our actual, and we're going to come up with 7%, 0.07. We're going to go ahead and copy that out. We were off by 7% there. 7%, 13, 6, and 2. And let's just go ahead and calculate our average there, which will be our MAPE. So we're going to do average, highlight these guys. So in this case, our MAPE is 0.07, 7%, which is the average of these values right here. All right, that's how we calculate MAPE. So to do it manually, though, you would just take the difference of these two numbers, and then, which is your forecast and your actual, and you would take the difference and divide it by the actual and come up with a percentage. And do that for each one of your values, and then just average those up, add them up, and then divide, in this case, divide by 5. 0.07, 0.07, 0.13, 0.06, 0.02. Add those up, and that would come to 0.35, and we would take 0.35 and divide that by 5, which would obviously come out to 0.07. There we go. Okay, how about our next one? What's the expected value under perfect information? Or if we had a crystal ball, how much money would we be able to make in this scenario? So these are the different strategies that we can choose, 1 through 4, and these are the different states of nature, or the different outcomes that could happen. So if I know this is what's going to happen, I'm going to choose whichever strategy is going to give me 360. If I know that this is going to happen, I'm going to pick the strategy that gives me 350. If I know this is going to happen, I'm going to pick this strategy, A3. If I know this is going to happen, of course, I'm going to pick the 250. So 60% of the time I'm going to make 360, 15% of the time I'm going to make 350, 15% of the time I'm going to make 400, 10% of the time I'm going to make 250. And it's just a quick bit of math here, and we'll have that one solved. Let's do that right. We don't need to do that in Excel. The answer comes out in this row. It's going to come out in this strategy. We're going to come up with 216, which is 0.6 times our 360. In this strategy, we have 15% times our 350 gives us 52.5. 15% times our 400 obviously is going to give us 60. And then 10% times 250 is going to give us what? 25. Add those up, comes to 353.5, which is the answer to this problem. All right, the next one is a little checkers problem. Checkers fries have a length specification of 4 inches, tolerances of plus and minus 0.4 inches, and the current process has an average length of 3.7 with a standard deviation of 0.06. What's the value of the CPK in this case? Is this process capable? Can they even make fries correctly with this process? All right, so if you take a look at page 355, look way up at the top, you're going to see the formula for calculating CPK. In this case, it's going to be the lesser, the minimum of, and we did this a little earlier, it's going to be your average minus your lower spec limit, and you're going to divide that by 3 times sigma, or your standard deviation, and then the other choice, you're going to take the less of these two. It's going to be upper spec limit minus your x bar, or your average, and divide that again by 3 sigma. So let's set that up in Excel. Again, this is a quickie on a piece of paper as well, but let's set it up in Excel and see how it comes out. Our average that we know from our testing was 3.7 inches, so we'll say 3.7, and we want to subtract our lower spec limit. And our lower spec limit, if you think about it, the length spec is 4 inches, plus or minus 0.4. So 4 minus 0.4 is going to be 3.6 inches. 3.6 inches. Okay. And we're going to divide that by 3 times our standard deviation, which is 0.06. Okay. So that's one of our choices. Our next one is going to be the upper spec limit, which is going to be 4 plus our tolerance. It's going to be 4.4 inches minus, in this case, our average, which is going to be 3.7 inches. And again, we're going to do the same thing here. We're going to divide that by 3 times our standard deviation, 0.06. And our answer is 0.56. 0.56? What the heck does that mean? Well, we know that if the process capability index is less than 1, that we've got a problem. And in this case, if you just remember that the average length is 3.7, where their spec is 4 inches, that we've certainly shifted toward the lower end of the range. So we've really got a potential problem here with our fries. So, all right, well, that's how we calculate it. And again, we'll take a look at that formula. It's the minimum. Now, you don't have to use the minimum. If you're doing this by hand, just do this math here. 3.7 minus 3.6. Divide that by 3 times your standard deviation. And then compare that to 4.4 minus 3.7 and divide that by the same value that you came up with over here. And whichever one of these, either this one or this one, is lower, is going to be your CPK. In this case, it's 0.56. Next question is number 16. We've got just a quick linear equation here developed from a regression, from the regression formula, or you could use slope-intercept in Excel to calculate the same things. It's our intercept, and here we have our slope. So in this case, we have regression. We're going to predict umbrella sales based on annual rainfall. The equation is y equals 1200 plus 57x, where x is, no, not advertising dollars, where x is rainfall, of course, and y is sales. So if rainfall is 35 inches, what is the prediction for sales? All right, well, let's jump to our good buddy Excel. And this is a slam dunk easy problem. All right, we're going to say equals 1200 plus 57 times 35. Bam, 3195. So we have our 1200 from our original problem, and the 57 was given, and we're just going to plug in, instead of the x, we're going to plug in the 35 inches for rainfall. And if we have 35 inches of rainfall in a certain year, we're going to sell 3,195 umbrellas. Now that would probably be more like 3,195,000 umbrellas if you're a large manufacturer or somebody like that. But let's move on. Our next one asks us, how do we interpret a CPK? And a lot of times people will say, well, that just means the process is not capable. Not necessarily. The process might be capable, but you still might produce defects because it's not centered properly. You may have a really tight process that doesn't have a lot of variation, but if it's off center, if it's shifted way down, you might be inserting a certain quantity of product into a jar, and you are almost always exactly the amount every time. Every jar has the same amount in it, but you could be putting too little in almost every jar or too much in almost every jar. So the process is capable of doing a real tight range, but the range, just the actual mean of it, might be off. Since we have it here, let's just talk about what is not part of a decision tree, and that's going to be expected opportunity loss. These other things, decision points, states of nature points, conditional probabilities, and branches, are all certainly part of a decision tree. Make sure you take a look at these pieces in the text and understand what the different boxes and squares and things like that are for decision trees, what they mean, what types of values go in the various places. And then finally, we have a kind of a similar one here, product design specs required by the customer. We talk about that up here in our other ones. In our checkers example. So we know that the customers expect the fries to be about 4 inches long and plus or minus 0.4, and those are called tolerances. That's what the customer will tolerate, the variance that they will tolerate in the product. And then finally, last but not least, what sort of data and components are needed to create an exponential smoothing model? Well, we know we need alpha, and we need our forecast, and we need a prior value, and the alpha is going to put a weight in the formula. The larger that alpha, the further we're going to move each time in the direction of the error that we have from the previous period. Okay, well, again, guys, I've really enjoyed this semester with you, and hope to see you guys out in the real world, and hope to hear that all of you have graduated and done great things, and have made us all proud here at Georgia State.